Autoionization of water, the most fundamental step in aqueous chemistry. Every beginning chemistry student learns this deceptively simple reaction. The way it occurs is intricate and fleeting, but with specially designed rare event sampling, it has been captured by computer simulation. This video shows one example of the autoionization process discovered in that way. It is shown in extreme slow motion, revealing action that occurs within 150 femtoseconds. That's less than a trillionth of a second, a time in which light travels only 1/10 of a millimeter in vacuum. Let's watch it again. Each water molecule has one oxygen atom and two protons, attached by covalent bonds. Neighboring water molecules interact through hydrogen bonds, exerting electrostatic forces of directional adhesion responsible for many of water's peculiar properties. This movie focuses on dynamics occurring along a wire of such bonds, highlighted with color. Keep in mind, however, that these motions are driven in large part by what's going on in the environment of surrounding molecules. As dynamics proceeds from this initial configuration, protons will move along the highlighted wire, and colors of the water molecules will change to help us resolve where protons are moving. Blue coloring highlights the hydroxide ion, an oxygen atom bound to just one proton. The yellow oxygen atom is bound to 3 protons. That's a hydronium ion. Let's see that again. The initial movement of protons along the wire is prompted by a rare fluctuation in voltage, produced by an unusual arrangement of surrounding molecules. Its structural basis is collective and too subtle to pick out by eye. The important thing is that the voltage is transiently large enough to destabilize an OH chemical bond. The voltage fluctuation does not last long, not even 1/10 of a trillionth of a second. In the rapid charge separation it spurs, each participating molecule along the wire seizes a new proton from one neighbor and relinquishes another proton to the opposite neighbor. If nothing else happens, this collective proton translocation will proceed in reverse as the voltage fluctuation disappears, leading back to the ion-free state. What does happen in this trajectory to fix the charge separation is a change of allegiance of hydrogen bonds. Let's see that again. The hydrogen bond wire breaks, blocking the original route for recombination. Different routes along other connecting wires are available, but they are less passable. Separated charges can now diffuse apart even after the transient voltage disappears. This example trajectory was drawn from theoretical calculations. It illustrates just one way that the interplay among electric fields, proton conduction, and hydrogen bond rearrangements can result in charge separation. When will these features be examined with natural experiments? Spectroscopic signals exist in principle, but measuring them amidst the background signals of more common dynamics in water presents a significant challenge. Meeting this challenge will clarify the inner workings of one of water's most fundamental processes.